Today we've introduced the sequence. Okay, sequence A1, A2, A3, a function which the domain is all the positive integers. Okay, so today we're going to continue and finish the sequence. So first one, we're going to look at a monotonic sequence. Okay, just monotonic. So what is monotonic sequence? Mono, you can think about mono as what? Is multiple is several. Mono means single, like okay. Monotonic sequence is a sequence AN is monotonic if its terms are non-decreasing, which means A1 is less than equal to A2, less than equal to A3, less than equal to continue, less than equal to AN, less than equal to continue. Okay, so for example, AN equals n, you can know A1 equals 1, A2 equals 2, A3 equals 3. It's always increasing, okay, it's non-decreasing. So you got 1 less than 2, less than 3, less than 4. It's increasing sequence, okay, it's a non-decreasing sequence. Or you can go up, always go up, or you always go down, right? You have two directions. Or if its terms are non-increasing, basically this one means A1 is bigger than equal to A2, bigger than equal to A3, bigger than equal to A4, continue, bigger than equal to AN. So all the sequence is continuous or decrease, and it's decreasing, okay? But it's not continuous. It's like a dot n equals 1 equals 2 like that. But it's decreasing, okay? And we can also look at example AN equals 1 over n. So A1 equals 1, A2 equals 1/2, and A3 equals 1/3. You can see this sequence is 1 bigger than 1/2. This is A1, A2, bigger than 1/3. It's bigger than continue. It's always bigger than the next one. Okay, it's non-increasing. Okay, non-increasing sequence. So this is a monotonic sequence definition. Okay, and then look at the first one. A sequence is bounded. The sequence is bounded above. Okay, a sequence AN is bounded above. A sequence AN is bounded above if there is a real number M such that AN less than equal to M for all n. Okay, so basically the sequence is bounded above. You have all that for a real number AN less than equal to M for all m, and then the number M is called a up boundary or up bound of the sequence. Okay, the upper bound of the sequence. Okay, so basically all of them is less than 1. For example, you can look at 1 over n. If you have an equals 1 over n, well, you know that an is always less than equal to 1. You can say that this sequence is decreasing. Suppose n equals 1, so it's 1 is here. So it's decreasing. Then we do have a bound, upper bound is m equals 1. You see that, right? So for all the n, an is less than equal to m, so m is going to be the upper bound. Okay. On the other hand, we also have a bounded below definition. Okay, in the same way, a sequence a sequence an is bounded below if there is a real number n such that n is less than equal to an for all n. Well, it's just a definition. It's kind of like your common sense. It's not really a mathematical thing. If you have a sequence, it's bounded below, which means all the an has to be bigger than that number, okay, for all n. So then the number n is called the lower bound of the sequence. You can look at an example, an equals n. Well, you can, this one, you got first one, a1 equals 1, a2 equals 2, a3 equals 3, a4 equals 4. You have continue, okay, it's always continuous. But then this one will have a lower boundary, not boundary, lower bound, okay. So all of the other terms are bigger than equal to 1. So you can see this one, the below boundary, n equals 1. This is the like a lower bound, okay, lower bound of the sequence. Okay, so number 3. A sequence is bounded if it is bounded above and bounded below. A sequence an is bounded if it is bounded above and bounded below. Okay. If it is bounded above and bounded below. Okay. Do we have a sequence bounded above or and bounded below? For example, if you have an equals 4 minus 1 over n. Okay, so you can tell an for sure is less than 4. So you can set up 4 as a boundary, so as a lower upper bound. Okay, 1 over n is a positive number. 4 minus 1 over n, no matter what n is always n is integer, right? N is positive integer. So n is bigger than 4, is less than 4, but also bigger than 3, equal to 3. You can set up for the example this one, a1 equals 4 minus 1 is 3, a2 equals 4 minus 1/2, which is 3 1/2. Okay, a3 equals 4 minus 1/3, which is 3 2/3. Okay, so basically it's the 3 plus n. You got a your minus 8. You can an equals, okay, 3n n. We can change it to 4n minus 1. 4n minus 1. You can change that. You can do that. Okay, so you can always have this is less than equal to 3 2/3, 3 over 4, 3 4 over 5, 3 5 over 6. Okay, you always have the final is 3 plus n minus 1 over n. Okay, it's the same idea. You change 1 into n over n. So basically, an has a below and a boundary below, okay, lower bound, and also have an upper bound. Okay, the sequence is bounded. So next we're going to look at a theorem. If a sequence an is bounded, if it has a lower bound, upper bound, so it's bounded, and also monotonic, either non-decreasing or non-increasing. Like that, monotonic. Then it converges. Okay, this theorem is what you have to know. If a sequence is bounded and monotonic, then it converges. Okay, but it's not always you have to use this theorem to determine if a sequence is converged or not converged. Okay, it's a theorem you can use, but you don't have to always use this theorem to determine if a sequence is bounded, it's converged or not converged. Let's look at example. Okay, example. An equals 5 minus 1 over n, still very similar example. Then we can tell this an, we got an is less than 5. Okay, it has a lower bound. An is less than 5. It has an upper bound and also have a lower bound. So an is less than 5. It's bounded. Okay, now we got an plus 1 equals 5 minus 1 over n plus. So my question here is, can anyone tell me an and an plus 1, which one is bigger, which one is smaller?
An plus 1 is bigger.
An plus 1 is bigger. Why is an plus 1 bigger?
Because the an's by themselves are just going to be the same value, but when you add the 1 to the right side there, it's always going to put it up the 1 unit.
Okay, so basically you compare 1 over n and 1 over n plus 1. 1 over n plus 1, this denominator is less than 1 over n. So both subtract a number. From 5, you subtract a number. An plus 1 subtract a number, which subtract a smaller number. So the remaining value is bigger. Does that make sense? Since n plus 1 is smaller than 1 over n, so 5 subtract a small number makes the whole thing bigger. 5 subtract a bigger number, the whole thing will be smaller. Okay, so you got an is always less than equal to an plus 1. This means you got a1 is less than a2, a2 is less than a3, a3 is less than a4, and a4 is less than a5. You always have an less than an plus 1 is non-decreasing. Okay, it's monotonic. Okay, it's increasing always. So it's monotonic, it's bounded. So we can tell this sequence this sequence converges. That makes sense, right? It's bounded because it's the whole. If it's less than 5, bigger than, you can say -5. As long as you have a upper bound and a lower bound for it, it's bounded. Okay. So from here you can do many things. You don't have to exactly use this one to say it's bounded. You can say an is less than 5 and it's bigger than equal to 4. It's okay if you do this. You said it's bounded. That's fine. You can say an is less than 5, bigger than 0. That's fine. You can use this to say, okay, it's bounded. As long as you have a upper bound for it, lower bound for it, that's fine. It doesn't mean that the boundary has to be just a very specific number. Okay. So if it's bounded, you have to just find out a bound for it. Not have it has to be okay exact that bound where it stops. That makes sense, right? Okay. But you have to make sure this one and this one, the upper bound and lower bound is kind of like is correct bound. Okay. It doesn't have to be you say exactly okay it is bigger than 4 or less than 5. As long as you find that sequence is less than a number, bigger than another number. Basically, you need to do an is less than m, bigger than n. As long as you have this thing happen, it is bounded. That makes sense, right? And m can be any past any number, mb can be any number. As long as it has a interval, like a bound for this am, it is bounded. Okay. All right. So next one, I want to use this theorem to do an equals 5 plus 1 over n. See if you can do this one. I'll give you 2 minutes to finish this one by yourself. Okay, so I would like a student to help me to finish it. Do we have any volunteer to help me finish this one? Lacey?
I think it is bounded between 6 and it decreases between 6 and 0.
Okay, so we can just do this. Would that be okay? Yeah, you can do that. AN is bigger than, less than 6, bigger than 0. That's okay too. You can do, as long as you can find an upper bound and lower bound for it, that'll be fine. So the absolute value of AN is for sure.
But I think the lower is 5, not 0. 5, not 0.
Okay, you can do 5. That's fine. Yeah, you have a lower bound and a upper bound. That'll be enough. I think less than equal to. Okay, so you have a lower bound and an upper bound for it, so it's bounded. First, it's bounded. That's great. You prove that it is bounded. Okay, the second. We have to prove this is monotonic sequence. Is it monotonic sequence?
Yes, it is.
So why is it monotonic sequence?
Because it keeps like decreasing.
It's keep decreasing. Okay, so AN bigger than AN plus 1. Because 5 plus 1 over n bigger than 5 plus 1 over n plus 1, right? They both have 5, but this one is bigger than the n plus 1. So AN is bigger than AN plus 1. So this is a monotonic sequence, okay? It's a decreasing sequence. So then we have first and the second bounded monotonic sequence. Therefore, the AN converges. Makes sense, right? Okay, let's look at one more example. Thank you very much, Lacey. Next example, AN equals 1 over 3 minus 1 over 3n plus 1. So still, can you find this one? Use the monotonic theorem to prove it converge. Alright, I think it should be done now. So first we prove this sequence is bounded. So can anyone tell me what did you find for the upper bound and lower bound? Bigger than 0, right? I mean, n equals 1 is 1/3, right? So it's always positive for sure because this number is less than 1/3. But less than?
I think it increases from 0.2 to 0.3.
Yeah, you can prove that it has a bound. It is bounded. Okay, AN is bigger than 0, less than 1/3. It's bounded. Okay, it's bounded. On the second, AN and AN plus 1. Which one is bigger? Which one is smaller?
AN plus 1 is bigger than AN.
Very good. AN plus 1 is bigger than AN. Well, sometimes you don't know which one is bigger, which one is smaller. You say, oh, I don't know. So how about you just do this? Say n equals 1. Just compare A1 and A2. just compare the first two. You can tell A1 is 1/3 minus, you can do 1/3 minus 1/9. Then this one is 1/3 minus 1/227. So just compare simple ones. Compare A1 and A2, and then you can tell A1 is less than A2. You can do a few, and it's always true. But you can mathematically you can prove that AN is less than AN plus 1. Okay, because 1/3n is bigger than 3 plus n. This one, so AN is 1/3n. This is bigger than 1/3n plus 1. Okay, but if subtract a big number, so the subtraction, then the result is smaller. And then from 1 and 2, we prove this is bounded sequence. This means monotonic sequence. So therefore, this sequence converge. That makes sense, right? So basically, you just need to find out this sequence. First, the sequence is bounded. Then the sequence converge. Sorry, the sequence is a monotonic sequence. Then it converges. That's how you do the use this theorem. I think it's pretty straightforward. All right. So next one we're going to do section 9.2 series and convergence. Okay, so what is the series? We have to do a sequence. Sequence is A1, A2, AN, and then the series is a summation of all the terms. Okay, sum n from 1 to infinity AN equals A1 plus A2 plus A3 plus AN. Continue add until infinity, until A infinity, continue. Okay, sequence. So we got S1 equals A1, summation of the first term. S2 means add the first two terms, equals A1 plus A2. Okay, S3 means the summation of the first three terms, A1 plus A2 plus A3. And Sn means the first n terms, A1 plus A2 plus A3 plus AN. Okay, so for the infinity series, we call the sum as a series. Okay, so I have Sn equals. You can also use a notation as from n from 1 to n, n from 1 to n, and AN. Okay, summation notation. This is summation notation. Add n, AN, A2, A3, A4 until AN. This means the summation. Okay, so now let's look at the sequence. Let's look at the theorem. If the sequence of the partial sum Sn converge to S, then the series n from 1 to infinity AN converges. Okay. So S equals A1 plus A2 plus AN plus continue. This is the series from n from 1 to infinity. Okay, continue. And Sn, so you can also write this as n from 1 to infinity AN. Okay. If Sn diverge, if the first n terms also already diverges, then the series diverges. Okay. Now let's continue. Find example. Example, we'll look at a series. Okay, find m from 1 to infinity 1 over m minus 1 over m plus 1. Okay, so we want to find the series, the series of from 1 over m minus 1 over m plus 1, the summation. So we'll do, so S equals, you add all of them together. So you add A1 plus A2 plus A3 plus A4, continue, plus AN. Okay, so we want to know that what is S. So let's do, see what is Sn. Sn is from n from 1 to n, okay, An. So equals, A1 is 1 minus 1/2, A2 is 1/2 minus 1/3, A3 is 1/3 minus 1/4, continue, plus, and last one is 1 over n minus 1 over n plus 1. Sn equals this. That makes sense, right? So first n terms add together. 1 minus 1/2, the first one. Second one, n equals 2. So 1/2 minus 1 over 2 plus 1. Third term, 1 over 3 minus 1, 3 plus 1 is 1/4. Now, what do you see from here? Can anyone tell me what do you see? What do you see from this six-base summation? Okay, so what do you see? Negative 1/2, positive 1/2. What happened? Negative half, positive half. Does this cancel? All of them are cancelled. So you only have, it's 1 minus 1 m plus 1 over m plus 1. So now let's look at what is the summation. N goes to infinity, Sn, which is S, right? Sn, n goes to infinity. So the S equals n goes to infinity, Sn is a limit. N goes to infinity, 1 minus 1 over m plus 1. Now you can tell me what this summation is. So n goes to infinity, 1 over m plus 1 equals 0. So this is 1 minus 0, and I give you the final answer is 1. And then we got the series. The series converges to 1. Okay. Does it make sense? Let's look at a geometric series. Does anyone still remember what is a geometric series? Then the first, an over an plus minus 1. Okay, there is a common ratio between the two terms. Okay, geometric series is first one is a1, Second one is 8 times the ratio. Third one is 8 times the ratio square. Fourth one is 8 times ratio cube. So continue. This is the geometric series. Okay. For example, 2, 4, 8, 16, 32, 64, 128. Then continue 2 to the power n plus 1. So continue. So this is a geometric series. They all have a common ratio between two terms. So what is the geometric sequence, the series? Okay, geometric series, this is a sequence, it's not a series. Series is the summation. So geometric series A plus AR plus AR square plus AR cube plus continue plus AR n minus 1 plus continue. Okay, so basically this is you have a common ratio between two, but if you add everything together is a geometric series. Okay, geometric series is you have the summation. Sequence is 1 by 1, AR square. This is sequence. Okay, sequence is just 1 by 1 continue. Series is to add all of them together is a series. Okay, yes, the geometric series is A plus AR square, add everything together, equals n from 0 to infinity AR to power n. The first one is AR0, so it's A plus AR plus AR n minus 1 plus. Okay, this is a geometric series. So what happened with this geometric series? We have a theorem for the geometric series. A geometric series with the ratio R diverge if the R is bigger than or equal to 1. That makes sense, right? Because your ratio is bigger than 1, you keep multiply by a number is bigger than 1. Multiply by a number is the ratio which is bigger than 1. For example, if you 2, it's continue increasing. The sequence itself, the last term, it goes to infinity, not mention that series. The series, they add all of them together. Your ratio is already bigger than 1, or less than negative 1. Your ratio is already bigger than 1. If you add all of them together, it goes to infinity or negative infinity. Okay? Because the last term is already a very big number. You add all of them together, for sure it's going to diverge. That's very serious, that's very obvious thing, right? It diverges if it's bigger than 1. How about if the R is less than 1? If the ratio is less than 1, bigger than 0, then the series is a summation. Okay, just remind you again. Series converge to the sum. Why does the series converge? It's not just because the last term goes to 0. Because you multiply by a fraction which is less than 1. For example, multiply by half. You continue decreasing. In the end, is close to 0. Okay, but it's not just because the last one is 0. Okay, but how we got this is converged to. It converges the sum equals A. Sorry, I missed the A here. So it's A over 1 minus R. If the ratio is less than 1, bigger than 0, then the series converges to A over 1 minus R. Okay. Why is this one converges to A over 1 minus R? Let's just do a simple work. So Sn equals A plus AR plus AR square plus AR n minus 1 plus AR n, or just A minus 1, because first one is AR 0, right? Okay, so what do I do next? I multiply both sides by Rn, sorry, by R, just by negative R. Multiply both sides by negative R. Then the first one, A will be, can anyone tell me what's the first one? What's the first term? If I multiply by negative r, the first one is what?
Negative RA.
Negative AR, that's right, negative AR. The second one will be
Yes.
negative, because I multiply negative r, right? So negative AR squared. Okay, this is the proof. Why is like that? Okay, so AR squared. Okay, and we also have, next one is minus, always a minus. Minus, I do have AR n minus 1. What about the last one? AR n minus 1 multiplied by negative r. The last term. This is from the previous one, right? And you have one more. This one goes to negative a r to a power. Nth power. Very good. So I got this too. What do you think I need to do next? What do you think I need to do next? Negative, positive, negative, positive, negative, positive. What do I do? What do you think I do next? Zijian?
Cancel out all the terms.
Yeah, cancel. How do I cancel it? By adding them together, right? At the top, add one by one. Add all of them together. Make sense? So you add the top, you add this two, positive, negative, positive, negative. How do you cancel? You have to add them together, then you cancel it. Okay? So you add it. Sn minus Rsn. So you get Sn minus Rsn. A, add, there's nothing here, so it's still A. AR plus negative AR canceled out. AR squared plus negative AR squared canceled out. This one canceled out. Everything canceled out. But I still have the first term for the first equation. The last term for the second equation. So minus ARN. That makes sense, right? So this one have a common factor, which is Sn. Sn 1 minus R. This one also have a common factor, A 1 minus Rn. Okay, and if R not equal 1, if R does not equal 1, if R equals 1, it's the same sequence, A, continue many A's, right? If R not equal 1, then I can divide both sides by 1 minus R. So A 1 minus Rn 1 minus R. Okay, so I get Sn equals, I solved Sn equals A 1 minus Rn 1 minus R. Okay, so first thing, if R is bigger than 1, if R is bigger than 1, I'm going to look at this sequence. Limit n goes to infinity, so this S, the series S equals n goes to infinity Sn equals limit n goes to infinity 1 minus R A times 1 minus power Rn. Okay, if R is bigger than 1, does this one converge or diverge? Does this one converge or diverge? If R is bigger than 1. Diverge. Okay, diverge. If R is bigger than 1, this diverge. Because R to power n goes to infinity. Okay, this one will diverge. Alright. You can also factor the top. You know that. I just give a little bit help. If you don't, you can do a little bit more help. You work like this. you can factor top as 1 plus r, 1 plus r plus r squared continue, and cancel with the 1 minus r. So this one you can continue that, and this cancel. I still have a, and then the r is bigger than 1, is bigger than 1 power. So goes to infinity is infinity, so this will diverge for sure. Okay, so if r is bigger than 1, it diverge. Second one, if the r is less than 1, then I still have the s, n goes to infinity, Sn, this is a limit, n goes to infinity, 1 minus r, a times 1 minus Rn. If r is less than 1, then the Rn, n goes to infinity, equals 0, right? If r is less than 1, you got 1/2 to infinity, this goes to 0, right? This goes to 0. So the a 1 minus r equals a 1 minus 0, because r infinity is 0, n goes to infinity, and over 1 minus r. So the final answer is a 1 minus r. If r is less than 1, then r infinity goes to 0, because r is less than 1. Okay, you continue to multiply by as a number is less than 1, so then it goes to 0. Okay, you have this one. If r equals 1, then you get Sn equals a plus a plus a plus continue plus a, which is Na. Well, n goes to infinity, then this whole thing will diverge for sure. N goes to infinity, Sn equals limit n goes to infinity, n times a. N equals to infinity, a times infinity, well, this goes to infinity, it diverges. So I proved that this theorem, the theorem I have in the front. Okay, so the geometric series converge if the ratio is less than 1. The ratio absolute value of the ratio less than 1, it converge. Okay, if the absolute value of the ratio is less than 1, it converge. If the absolute value bigger than 1, it diverge. It's geometric series. Okay, this is the proof. Okay, you don't have to know the proof, but you have to know how to apply it, how to use the theorem to prove, to say if the sequence diverge or converge. Okay, 1, 2, 3 is not exact. Is not I not require you have to prove this, but you have to know how to use the theorem to do the example, to do the to determine if the series converge or diverge. For example, series n from 0 to infinity 3 times negative 6/7 to n. Okay, so first, what is the ratio? What is common ratio? R equals what? Question. I have a question here. Can anyone tell me what is the ratio here? R, what is R?
-6/7.
-6/7. Yes, -6/7. Perfect. Thank you very much. So the absolute value equals 6/7, which is less than 1. The ratio is less than 1. This is a geometric series. It's AR. The geometric series is n from 0 to infinity ARN. Okay, this is a geometric series, and R is less than 1, and we know this one will converge. It converges to where? To what? S equals A over 1 minus R. A equals 3. R is -6/7, so it's 1 minus -6/7, and then it's going to be 3. 13/7, so the answer is 3. Keep changing, flip. 7, 13, so the answer is 21/13. Then we're done. The series converges to 21/13. Okay. I think you do have a lot of examples, not many, but you do have several examples about series converge or diverge in your homework. I hope you can practice, use the homework to practice. And we're going to see more examples next Monday. Tomorrow we're going to look at the homework 5. And next Monday we're going to continue finish the section 9.2, the series. Okay. Today we have introduced the geometric series. And I'll see you tomorrow to finish the homework 6. Okay. Thank you very much. I'll see you tomorrow.